Good evening. I'm Doug Arnold. I'm the director of the Institute for Mathematics and its Applications here at the University of Minnesota. And it's my great pleasure to welcome you to the second public lecture in our series, Math Matters, for the year. Today we're in for a real treat, a talk by Dan Rockmore on a nexus of mathematics and art. Dan is a professor of mathematics and computer science at Dartmouth College. He received his undergraduate degree in math from Princeton and then went on and got his PhD also in mathematics from Harvard. That was 1989. He's involved in an unbelievable range of projects. He's an expert in what might be called the most important algorithm, numerical algorithm of all time, the fast Fourier transform. And he's written many papers and several books on applications of fast transforms to things like climate modeling, signal processing. In 1995, he was awarded a 5-year presidential faculty fellowship from the White House for his excellence in education and research. He's a co-founder, together with several neuroscientists, of the fMRI Data Center at Dartmouth, which is a publicly accessible database of brain images. And his work on digital art authentication, which we'll hear more about tonight, has been reported in the New York Times, Newsweek, the Washington Post, and essentially every major newspaper. Dan's also nationally recognized as a superb expositor of mathematics in many different formats. He's written numerous articles for newspapers and magazines. He's a commentator on Vermont Public Radio. He's a co-producer of a full-length documentary film, The Math Life, which was released in 2002 and shown on most public television stations across the nation. And he's currently producing 2 more films to come out this spring, Living Math, about mathematical biology, and Happy Birthday Hal, about artificial intelligence. And with all this, he's found time to write a wonderful book, Stalking the Riemann Hypothesis, published by Random House and available at your bookstore. And last but not least, Dan is known as a talented lecturer. You'll be able to see that for yourself very soon. And so, without further ado, I give you Dan Rockmore.
Hello? All right, good. Thanks for the nice introduction, Doug. It's a pleasure to be here. So I'm going to talk to you today about, it's true, some funny connection, interesting connection between art and mathematics, and it was picked up by a lot of papers. People like that nexus somehow. You know, everybody views the mathematicians as being cold and calculating, and the art world as being all warmth and spirit, and if you can connect them in some way, then the media goes nuts sometimes. But the mathematics of it is actually, I believe, quite simple. It's sort of a current standard techniques, and it's all about the quantification of style, and I hope everybody understands it and enjoys this. So let's hope it works. Sorry. Great. So in May of the past year, this was a headline in the Times Arts and Leisure section. I think it was Memorial Day, actually. And is this a real Jackson Pollock? A filmmaker, Alex Matter, claimed that he had found 32 Jackson Pollock paintings in a storage locker out on Long Island. They had been there for several years, and he was just coming forward to tell everybody he had them. And so he announced it very publicly, and there were some reasons to believe it. In fact, his family was known to be friendly with Pollock when he was alive. His father was a photographer, his mother was an artist. So there were lots of family connections, and the claim was that Pollock had given these paintings to the father at some time, and the father only revealed these very late in life to the son because he was afraid that his wife was going to sell them off. So there was a story there, and if you look at it, you know, I'm not an expert in Pollock. Maybe, I don't know if anybody here is an expert in Pollock, but you might believe it. And the story's not too bad. You might believe that too. And you could do a lot of testing, which is what you often do in authentication. You test materials. You even hire a private eye to check out the story. And then you have people who've looked forever at Pollock's come and take a very close look. You know, would Jackson have done that? You know, and then somebody says yes or no. And people either agree or they don't agree. It's not a proof, as a mathematician would like. Now, the interesting thing about this story is that there actually is somebody weighing in using mathematical tools on this particular set of proposed Pollocks. And in a great synchronicity of time and space, the announcement occurred today of whether or not these are real. The testing is done by a physicist at University of Oregon, Richard Taylor, and he's been sitting on this result for quite some time. That's a totally other story. So I'll be able to tell you the answer. When I arrived here, I wasn't able to tell you the answer. I knew the answer, but I was sworn to secrecy. But now it's out, and I can tell you the answer. So Pollock or not, and one person weighing in with a significant voice to the arts community is somebody using mathematics. So Richard's work and the work that I've done with my colleagues falls within a much larger framework. It's an area which collectively has been come to known as stylometry. And generally speaking, the question that we're asking here, is there a method of quantifying artistic style? And more generally, you can ask, is there a method of quantifying style, whatever that means in the particular context of which you're thinking about. So what I'd like to tell you, and I'd like to tell you a little bit about sort of this much larger world today. So I'll tell you a little bit about literature, which is where stylometry came from. Tell you a little bit or much more about painting, the stylometry of painting, which is a much more recent recently developed field. And I'm actually not going to mention dance at all except for this moment or movement, because there's been this terrific workshop this week, and there's a whole collection of people at the IMA who know much more about this now than I do. But the question of whether or not you can quantify the style of movement is something that animators have been doing for quite some time, and they've been doing it by hand, and now it's all done digitally by mathematics using the technology of motion capture and various tools from probability and statistics and dynamical systems. So this is there's a huge body of work that I could talk about, but in the interest of time, I'm just going to focus on the first two. Okay. Can people still hear me when I step away from the mic? No. Okay, so I'll try to stay here and speak out. Okay. All right, so first things first, stylometry, writing by the numbers. So stylometry is an old subject. As you see here, it dates from 1850. Now, everything that I'm going to be speaking about today is statistics in some way or another. Okay, so numbers attached to artistic output. So it's not a terrible surprise that literature was the first place where people tried to count things and make some mathematical arguments about who might be generating the output, because literature gives you something to count immediately. It gives you words, it gives you letters, it gives you sentences. So in the 1850s, Augustus de Morgan, who people may know from set theory, de Morgan's rules, he thought that he would be able to discern the difference between letters written by two of the saints, I think, in fact. So he thought that if he looked at word lengths, he was sure that one had a predilection for long words, one had a predilection for shorter words, and he thought that just by looking at those statistics, he might be able to tell the difference. And I think that in his letter, he writes, "If only I had a little money to devote to this project." Well, he didn't have a little money. He didn't have a graduate student either, I guess. And so he never picked up on this. But in the 1880s, Thomas Mendenhall, who was a physicist, a U.S. physicist, thought that he might try to, again, count words, okay, looking at word frequency. So here it's simply how many times per 1,000 words, let's say, did Shakespeare use a 4-letter word versus how many times in 1,000 words did Bacon use a 4-letter word. And he hoped that that might distinguish Bacon's and Shakespeare's writings, and in fact it didn't. But he published 1 or 2 papers around that area, and then nothing much happened. And then several years later, philosopher of history, Vincente Ludoslavsky, was interested in the problem of the chronology of Plato's works. So historians of philosophy are interested, when did a philosopher have a particular idea, to try to track their development. And so Ludoslavsky actually counted over 500 different sorts of things from Plato's dialogues and developed what he claimed was a natural chronology of Plato's works. Again, totally from word usage statistics. And he called this stylometry, and that was the beginning of a field officially, even though it had been going on for some time already. And it's continued on to this day. People use word statistics quite frequently, actually, to try to distinguish between authors or to assign authorship for particular documents. The biggest hit, I'd have to say, the one which made the most press, was probably the work of Mosteller and Wallace, who looked at a collection of papers called the Federalist Papers, which were written around the Revolutionary War, actually the time of when they were trying to ratify the Constitution, and they were written, they were published anonymously, even though everybody knew that they were written by John Jay, James Madison, and Alexander Hamilton, and they were written to try to get the New Yorkers to ratify the Constitution. So historians, after some time, were able to assign attribution to the majority of them, but some of them were still in dispute at the end, 12 in fact. And so using stylometric techniques, some sort of word frequency statistics attached to how words were used, they were able to assign the remainder of the papers to Madison, in fact. And this made quite a lot of, it was a big result when it happened. And generally, since computation entered the field, in the sense that literature was put on the computer, this is now a project that anybody can do, and anybody does. And there are journals devoted. There's a journal of computing and literature, for example, where people do these sorts of things, statistical tests. And and there are lots of good projects there for people who are interested. So I want to say a little bit about the techniques. So generally speaking, as I said, people look at word frequencies. So how many times per 1,000 words is a particular word used? And so there are 2 axes, if you like, for studying literature in this way. You could, for example, you could attend to rare words. That might be a reasonable signifier. I know, just because when I was studying for SATs, I learned the word avuncular and I learned the word alacrity. There's no other reason I would know those words, I'm sure, except years ago I was studying for the SATs. And so I use those words every once in a while. And they're not natural. Who in this audience has ever used the word avuncular in a sentence? All right, so that's a pretty good first discriminator. Now how about alacrity? All right, well, you and I still aren't distinguished, but generally speaking, rare words, okay, might seem reasonable to use. And in fact, so people may remember the story of primary colors several years ago. So the book was written Primary Colors, and the question was who wrote the book. And eventually Don Foster, an English professor at Vassar, determined that it was Joe Klein, and the way in which he determined this was he had some prior information about who he thought might have written it. But then he noticed that there were these totally nutty adjective constructions that were used quite frequently. And so he did some comparisons to a known body of work, and he targeted Joe Klein. So while that might seem a good way to do it, it actually turns out that a much more robust way to assign authorship is by looking at common words. And that, when I learned it, was quite a surprise to me. But it turns out that the way in which you and I use function words, and function words are common words. So as I've written here, prepositions, conjunctions, and so on. So words that are grammatical glue, if you like. The way in which you use those words actually seems to be a much better signifier of your style. Now, if anybody here has ever had a copy edit returned to them, okay, you see your style in the copy edit. You see the red marks around the misuse of which versus that, and however instead of nevertheless, and all these things, and you just do it over and over and over again. And there you are in red on the paper. And so it turns out that the glue is actually much better. And I want to attend to one particular instance of this in which function words were used, because I view the work that my colleagues and I do as being the visual analog, if you like, of the function word approach to stylometry. So one particular example, a fun example. So The Wizard of Oz was just one in a whole series. As many of you may know, there were 31 Oz books. And so Frank Baum generated one book a year for 14 years. In the 15th year, he fell ill and he died. Now, any good publisher would never let a good franchise die with its author. So somebody had to take up the Oz series. And eventually, someone was found, Ruth Thompson. And so there was this middle book that Baum had started. And then Ruth Thompson took over and wrote another, for sure, she wrote another 15 books. Okay, but the question remained, for the 15th book, who wrote that book? When it was first published, it was still published as Baum's book with a little note about Ruth Thompson. But over time, Thompson became more prominent in the attribution. But you could ask this statistical question. I mean, you could ask it as a statistical question. Who wrote that book? So this is all work of Jose Benongo, who I believe is now at Emory, and was reported in Chance News. And I want to describe it here for you. It's a terrific story. And this is the general methodology, if you like, for how many of these analyses go. So there are two sides, two known collections. Okay, so we have 14 books that are known in the Oz series, known to be written by Baum. We have 14 books in the Oz series known to be written by Thompson. They have 600 some odd thousand words and 500 some odd thousand words respectively. And this is where we're going to acquire our style statistics from the two authors. And so in this sort of approach, what you first do is you look for the most common function words, 50 most common function words in particular. And you then take the known corpus and you divide it up into word blocks, and in each of those, you look for the word frequency. So blocks of 5,000 words apiece, and you ask, and this is the training data, because this is what we know. We're going to look for we're hoping that there's a signature in these word blocks. So I now have these 223 blocks of 5,000 words apiece, so block 1, block I, up to block 223. And in each block, I can ask, what was the frequency of the word a? What was the frequency of the word as? What was the frequency of the word however, and so on. Okay, so each one of those is some fraction. Okay, the number of times however was used, let's say, divided by 5,000 is going to give you, in block 1, will give you F1 however. And similarly, for all the blocks up to block 223. So for each block, I get a list of 50 numbers, okay, which is somehow a measure of the style of this author. Now, a list of 50 numbers to a mathematician is actually a point in space. So you may remember from your geometry classes a long time ago, there was the Cartesian plane. In the Cartesian plane, you assign a point in space by being how much you move in a horizontal direction and how much you move in a vertical direction relative to some origin. Okay, so two numbers tell you where you are in the Cartesian plane. So mathematicians, nobody can see 50 dimensions, but formally I can think of a list of 50 numbers as a list in 50-dimensional space. Okay, so that might not seem so useful because I can't see it, so I don't know what I'm going to do with it. But we have tools to deal with this. And so really what I'm asking now, I'm trying to turn this into a geometry problem. Each one of these blocks is giving me a point in 50-dimensional space. Just think of 2 dimensions, okay? Your head will explode if you try to think of 50. Each block is a point in space. And so now there's a natural geometry question. Is sort of the region of space in which I've assigned the boundworks, okay, the blocks from the boundworks, is that separated from the region of space in which the Thompson points, the Thompson lists fall? Does that make some sense? All right, so I'm thinking of this entire corpus as 223 points in this 50-dimensional space and hoping that there's an Oz neighborhood and a Thompson neighborhood. So I can't see 50 dimensions. And 50 dimensions, some of those dimensions might not even be worth looking at, in fact. So what I do, and what mathematicians do, is we might use a tool of dimension reduction. Okay, so what I'm hoping is that of these 50 dimensions, maybe there are only 2 components worth thinking about. Again, you can think of in a 3-dimensional space where you can go up, down, side to side, and back and forth. Okay, that is also, there are various 2-dimensional spaces in there. Any plane is a flat thing, and so can be described by 2 dimensions. Okay, so that's a way of seeing 2 dimensions and 3 dimensions, and what I'm hoping is that there are 2 dimensions that will describe this 50-dimensional data in some useful way. So a nice analogy, okay, is, so the way in which we look for this is we're looking for the most informative direction. Okay, so a good analogy is the following. If somebody asked you, so they told you, look, I have a camel, okay, and I don't know if it has 2 humps or 1 hump, but I'm going to take a picture, all right, and I want you to decide from a picture. Now, you wouldn't tell them to take the picture straight on, right? Because unless, well, maybe the camel would have, 2 really fat humps or something. I mean, who knows? You wouldn't be able to distinguish them generally. But what you would do is a side view would tell you immediately. So that shows you that there's a preferred direction that's more important, more interesting to analyze the question. So of those 3 possible, in that 3-dimensional space in which the camel sits, some 2-dimensional vision of it would tell you 1 hump or 2 hump, and there's a preferred one. So similarly, for 50 dimensions, we want to do something like that. So the technical tool is called principal components analysis. That's what Benungo used. And so he's reduced this unvisualizable 50-dimensional space. He's taken the 2 most important dimensions, the sort of preferred plane, if you like, in this space. And this plane has the property, as we see on the screen here, that with a particular choice of axis, that all the Thompson works sit on one side of a line, and all the bound works sit on the other side of the line. This is of the works that we know. Okay, so what this tells you is that Thompson has a particular style, where that there is a neighborhood, actually, of Thompson works, and that there's a neighborhood of bound works, okay, over here, of the works that we know. So the next thing we do is we want to see, well, maybe this depends completely on the books that we chose. So what you might do, the sensible thing to do, is to confirm that this is a sensible discriminator. So these symbols up here refer to a collection of other books written by Baum, not Oz books, okay, but just written by him, so known to be in his style. And there also we do the same thing. We collect these lists of 50 numbers, and then we reduce them to 2 numbers in some fashion, and we plot them in this space. And we see that, again, they all fall in the right neighborhood. Okay, so that these discriminators actually seem to make sense. So finally, all right, now we believe that we have a good discriminator. Let's look at the unknown work. Okay, and lo and behold, okay, the Royal book, which is the disputed Oz book, falls clearly in the Thompson neighborhood. Okay, and just for comparison, another book known by Baum is tossed into the mix and again is clearly in the Baum neighborhood. So from statistics, okay, from this dimension, so we figure out what are sensible features. We then do some dimension reduction, and we take a look, and we have a reasonable statistical signifier. So if you had another book and you wanted to know, you'd do the same thing. You'd push it in the machine and see where it fell. Okay, does that make sense? So, all right, the Oz stories. Okay, so now I want to shift gears. That was literature, and again, there's a huge, I mean, I hate to tell you this, but you know, the NSA uses a version of stylometry to read your email automatically sometimes. You know, you write in a particular way. You have a style, and they can do that kind of thing. All right, so it's used in all sorts of contexts. So moving from literature to art, to the visual arts, rather, we have the analogous question. So we could ask, you know, so I'm given a painting and say, who painted this? The elephant? Probably not. We have reasons to doubt the elephant painted this. Oh, sorry, wrong key. Maybe Picasso, we have good reasons, or your cat. So we'd like to use the same sort of approach, okay? And the question is what, you know, features to extract, and so on. So the example that I'm going to talk about in this context is the one that my colleagues Hani Farid and Sui Liu and I worked on, and it was a question, and it was a question with a known answer. So Peter Bruegel the Elder is a very famous Flemish artist, and he has some beautiful drawings. Now, in 1900, the Catalogue Raisonné, which is the sort of approved list of works attributed to an artist, had 100 Bruegel drawings of this flavor in it. In the year 2000, when the last catalog was written, it was about 50. So over 100 years, there were 50 works which were slowly taken away from Bruegel. They were deemed imitations. You know, and presumably they weren't all done in a malicious way. It was often it still is the case that you will copy the master to learn how to draw, how to paint, and presumably some of these were just of the right time period, and you know, people didn't know any better. But so over time, the collection's been winnowed. And so I was lucky enough to know the woman, Nadine Orenstein, who curated the Bruegel exhibit at the Met in 2001. And so she was taking me around the exhibit and telling me about this problem, and you know, telling me, you know, well, we know this is a Bruegel because the trees, the leaves had this sort of characteristic 3, which he used, which looks like a 3, but he used it to make dense leaves. And she's telling me all these various sort of linear kinds of things, how she sees Bruegel. And it occurred to me that, you know, this is something that perhaps the computer might be able to do with some facility, and why don't we give it a shot? And my friends, Hani and Sui, had been working on the problem of can you detect on the computer a photoshopped image, so a photorealistic image versus a real photo of a natural scene. And so it seemed to be there was a good technique for a good problem, and so we began to work on it. So the question is, how to distinguish between these two? Again, if you're not a Bruegel expert, or even if you are, how is it that you're doing that? So this falls within the realm of authentication, and as I said with respect to the Pollock story, there are standard techniques, and they work quite well in many cases. Art history, you know, you need to know something about the artist, how they were working at a particular time. Does this make sense in their total corpus? People love to have documentation. A well-known painting, you will know every person who's ever owned it, every place it's been exhibited, every person who's ever touched it. And I mean, they come with a birth certificate and this tremendous provenance, so that you can be sure that the painting you have was created by the master. And also, there's connoisseurship. So people have been looking at Bruegels. There's a person who's been looking at Bruegels for 60 years, you know, and they've seen everything that Bruegel's done. Something doesn't smell right if they see one that isn't a Bruegel. But you might ask, is there a role for quantitative techniques? And I should say, I mean, this isn't, in many ways, this isn't the first time mathematics has been used, neither the work done by Richard on the Pollocks or our work on the Bruegels. But mathematics has been there, I mean, mainly under the surface in some ways. A materials analysis, so for an old painting, you'd like to know, are the materials 400 years old, for example? So by the same way in which we date many materials using various radioactivity measures, mathematics is under there. It's in differential equations. Similarly, in X-ray analysis, mathematics is there. It's Fourier analysis. It's the radon transform. But it's not prominent. More recently, people have used things like models for how the crack lines of an old master should be in an oil painting to determine if the paint really was laid down 400 years ago. And again, mathematics comes to play when you do signature analyses, which people do. The painting better be signed, and if it is signed, is it signed by the person that they claim it's signed by? But you would imagine that there's room now for new mathematical tools, and mainly because of digitization. I mean, every form of media now, in one way or another, can be put on the computer. And so it's a completely sensible question to ask, once this image, sculpture even sometimes, is resident on the machine, so now it's encoded as numbers, in those numbers, can I find the hand of the artist? If you could look on the screen and say it is or it isn't, one way, I mean, there's some gestalt that's going on, but nevertheless, it's a completely sensible math question to ask now. So one thing that I like about this sort of work is that it actually does sort of reach back to the beginnings of connoisseurship. So if you don't know much about connoisseurship, and I certainly didn't before I began this, you just kind of think, well, they're just looking, and then they want to know, does their stomach feel right or not, and then they'll make a decision. But the origins of connoisseurship actually are, I mean, they're scientific. Okay, they're not emotional, I should say, and so they date back to this man that we see here, Giovanni Morelli, who was an Italian statesman, an art lover, who came to the arts late in his life. He was trained as a doctor, and then he went off to hunt dinosaurs for years with Louis Agassiz. And so he was interested in anatomy generally. If you're hunting for dinosaurs and you find a bone, the question is, where did this bone go? All right, and that may be dictated by all sorts of small features in the bone, and sort of think of a bone as a function word, if you like. And so Morelli had this idea that he might be able to use those sorts of skills, distinguishing between anatomical features, to determine artistic signatures. And he had a personal stake in this. So he was working around the time that Italy was being unified, and he wanted to make sure that the artists of his homeland got their due, and if there was a lousy piece of art that was attributed to one of his neighbors, he didn't want that to happen either. So he decided to begin to weigh in on this. And so he wrote up, these are called schedules, and these are called Grundformen, is what he called them, so the elementary forms. He would copy the features of known famous artists, and he would create these books. And then if somebody presented him with a painting and they said, "I'm sure, Signor Morelli, this is by Botticelli," and he'd look at it, and he'd look at the ear, and he'd go through his book, and he'd go, "I don't know, Botticelli doesn't do ears like that. I don't think so." So he was doing this sort of feature comparison, which if he had a computer, it's completely obvious to me that he would have done this on the machine. So updating us now, another 100 years, we're trying to do this on the machine. So again, the technique that we used is the visual analog. I like to think of this feature vector approach for literature. Sorry, let me just go back there so first we have to digitize the works. Then we have to extract the features, the analysis, which we do using something called wavelets, a particular sort of time frequency analysis. After we extract those features, we're going to get lists of numbers, and then we're going to find some way to do a dimension reduction of these numbers so that we can visualize them in 2 or 3 dimensions and then make a declaration about false or true or false decision. So Bruegel. Our test set was, we used 13 landscapes. These are drawings where we knew ground truth. So 8 authentic Bruegels and 5 once thought to be Bruegels. They had been removed sometime in the last 100 years. And so step 1 is digitization. So we were working from color slides, which we scanned at as high a resolution as we could, and then took out a sort of central image within the scan to analyze. Okay, we didn't use the entire thing, but a pretty good chunk of it. And we didn't choose it for any particular reason. And then the last thing that we have to do is so in the conversion to numbers, so a color image, so even drawings are color. Okay, these in particular were scanned as color, but a color image is actually, for every pixel, every dot on the screen is actually 3 numbers. Okay, a red intensity, a green intensity, and a blue intensity. And you see that as one particular color. So every dot on the screen is then encoded as 3 numbers. We reduce this to a black and white image, okay, a grayscale image. So again, digital images, we think of pixels. Many people now have digital cameras, so we're comfortable with that idea. A pixel is really, for an image, is a number. And grayscale means that it's a number between 0 and 255. It's 1 byte, okay, 8-bit color, 8-bit grayscale rather. So 0 is no light, 255 is all light, so white. And so like a black and white, I think this is a Malevich, would easily go into a grayscale picture. So your picture, a black and white picture, is now a matrix, okay, of numbers, integers, between 0 and 255. Okay, so that's sort of as numerical as I hope we're going to get. Okay, so is everybody comfortable with that? When you take a digital picture, it's numbers that are encoded in the camera. So step 2, having reduced this to a black and white picture and a collection of numbers, is doing the analysis. So this is a particular small square from Pastoral Landscape, known to be by Peter Bruegel the Elder. And what I'd like everybody to attend to is, I'd like you to think of these. So this is really a collection of lines, is how we want to think of it. Okay, so they're lines of varying orientations, thicknesses, sort of densities of lines. Okay, and what we'd like to do is extract the statistics of this, sort of how horizontal is it up here? How vertical is it over here? You know, how sort of diagonal, kind of in between, is it maybe over here? Okay, those are the features that we're going to try to extract. So think of a line in a painting. If you just took it out of the painting, you don't know what it's part of. Okay, it's just a line. But that's, again, think of function words. Okay, if I tell you, well, I read something and it had the word nevertheless in it, you couldn't possibly reconstruct anything else that was going on. So again, it's that sort of analogy. So a visualization of what this decomposition does, okay, again, thinking of, I'm trying to extract linear elements, think visual function words, okay, is going to look like this. And I'm going to, let me see how those look on there. That's not terrible. Okay, well, we'll see a bigger one in a minute. So the idea is, again, to think of this image, okay, the central image is being composed of horizontal stuff, horizontal lines, vertical lines, and diagonal lines. The way that I like to describe this is, so many people grew up with an Etch-a-Sketch, okay? So you have that screen and it has 2 knobs on it, right, for moving horizontally and vertically. But you can make things that look better than squares and rectangles, right? And how do you do that? Well, you sort of move the horizontal a little bit, and you simultaneously move the vertical guy a little bit, and you start to get a line of an orientation that's somewhere in between. So what you should think of this wavelet analysis as doing is basically in any small region of the image, it's asking, on average, where are the knobs being turned? But 3 knobs. I'm going to give myself a knob to move horizontally, a knob to move vertically, and actually a knob to move at some orientation in between, which you wouldn't think a priori should be independent, but it actually is independent, okay, mathematically independent. And the results of that are these pictures down here. So for example, here I'm asking, you know, in any given region, okay, say up here, so remember, white is high intensity, black is no intensity. So a region that's white says that in that region, okay, the horizontal knob was turned very far, all right? And in this region over here, the horizontal knob was hardly turning, okay, because it's very black. And so you see what that picks up is you get mainly, okay, horizontal sort of features. Okay, there's a little in-between stuff, but mainly horizontal features. Similarly, when you look at the vertical, what I'm asking here in the image is where is the vertical knob in every small region? Okay, and that's a number. It's turned this much. Okay, and so that's each one of these dots in this image represents how much on average the vertical knob was turned in a small region around the center. Okay? And again, there's this in-between orientation, which you should think of as diagonal, but it's something in between. It's a little bit hard to describe. But the fact is that the combination of those three things is the image again. Okay? So again, each one of these images, okay, is a list of numbers. All right? And now I can ask for the statistics on those lists of numbers. Okay, and again, the analogy is, you know, how much was of used in this block, in that block, in that block, in that block, and so on. And then as a next step, you extract all these features. Okay, so this is the detail, and then effectively what you do is you blur the image. Okay, you blur the image, and the way in which you can think of this is as you're looking very closely at the picture, you're looking for fine detail, and then you put on glasses, and now the image is blurrier, and you're asking for sort of coarser scale features, and you do the same exact sort of test. Okay, how much vertical stuff is there? How much horizontal stuff? How much diagonal stuff is in the blurred version of the image? And you repeat this process of extracting features and blurring, extracting features and blurring, and you do this 5 times. So, having done this, okay, I get a list of numbers, and now what I'd like to do is to summarize those lists of numbers. So one summary might be in that image, what was the average horizontal content, for example? So if I average over all the tiny regions in that detail, what was the average amount the horizontal knob was turned? Okay, what was the average amount the vertical knob was turned? What was the average amount the diagonal knob was turned? And I collect those numbers as well as higher order statistics. And the upshot is that for every one of those pictures, like that little detail in the Bruegel, I get 12 statistics, okay? And I do that for 3 different scales, 3 different blurrings. So I get 36 numbers per detail, which are the marginal statistics. They summarize those knob turnings, if you like. We then collect a second collection of numbers. Now, these numbers measure something like the smoothness or the predictability in the image. And the way I like to think of this is that if we ask a collection of people in here to draw a tree like Bruegel, okay, then we all will draw a tree, and at a distance, they all might look roughly the same. Okay? But where they'll differ, again, is in the detail. Okay? And so the degree to which I can measure between the original and a blurry version that's predicted by some knowledge of what the knob turnings are, okay, is another place that I can look for features, okay? And this is, I admit, this is a slightly complicated idea, but we acquire the same statistics, again, comparing the original versus a prediction. This prediction, one more time, is created by looking at what those knob turnings were that we acquired in the first run of the data. And then from those knob turnings, we can ask a question, well, if I know everywhere sort of nearby this region exactly what was happening around it, would I be able to, how well could I predict what's happening in the middle? Okay, and then we construct this prediction, a linear predictor, and we measure the difference, and we look for the statistics in the difference. And again, we get 12 statistics per scale, and we did 3 scales, so we get another 36 numbers. So all that done, we extracted features, which again are trying to measure the linear nature of the picture, and we've collected 72 numbers, which we think of as a point now in 72-dimensional space. Now, remember in the Oz story, we cut the corpus up into 5,000-word blocks. So similarly here, we cut the image up into 64 non-overlapping blocks. Okay, and we take these and we acquire 72 numbers off of each block. So every picture now corresponds to a cloud of points in 72-dimensional space. Okay, so again, I have 64 lists of 72 numbers per image, and each one of those, and those 64 lists of numbers can be thought of as a cloud of points. Okay. So I have 13 images, which are now 13 clouds. And now, we're going to do something slightly different from the stylometry example. What I'd like to do is I'd like to measure in this unimaginable space what the distances are between these clouds. Okay? And then, once I know what the distances are, then we're going to visualize it. So there are many ways, actually, to ask what's the distance between two clouds. Okay? It's not so obvious. Do you find the sort, is the distance from the two closest points? Is it the distance from the two farthest points, or is it something in between? We actually use something in between called the Hausdorff distance for a certain reason. And, but what this allows me now to say is that this drawing is some distance away from this drawing in 72-dimensional space. Now that, if I just tell you that, you actually have a picture of that in your mind. Okay, you're thinking, all right, well, it's 7 units. All right, I'm thinking of it like that. And then I tell you, well, this guy's also 6 units away from this drawing. So now you're starting to put things in space. This guy's distance 6, this guy's distance 7. So I give you a whole collection of distances, a so-called distance matrix. Now I have to visualize this. So when we do that with the drawings, here's the picture that we get. The Bruegels are the blue dots. The black dot there is simply to show you the center of mass of all the drawings, in fact. And the red dot, the red squares, are the non-Bruegels. So it's really at this point nothing more than a proof of concept that this sort of technique actually does seem to create a region, a neighborhood, if you like, of Bruegel drawings from which non-Bruegel drawings are separate, and they're sort of statistically separate as well. Okay, so it's the same methodology. Extract features, find distances, visualize. Okay? And we're continuing this work in various ways. The current project is, I was given a collection of very nicely photographed Rembrandt portraits that the Met has, and it's the same story. When the Met bought each one of them, they thought they were all Rembrandts. Down the road, a third of them are definitely Rembrandts, a third are maybe Rembrandts, and a third of them aren't Rembrandts. So the question is whether or not this will work for oil painting is a much more complicated one, but we're carrying on. So I'm going to, so the last part of the talk it's the same area, but it's going to be a different technique. And it's the technique that Richard Taylor has used on Jackson Pollock. So, right. So Pollock is problematic for lots of people, I think. Many people, just see sort of randomness, okay, and no structure. But, many people see structure. Pollock said, I painted from nature, is what, I am nature is a famous quote of Pollock's. And there are all these, there's great footage of Pollock, dancing around his canvas and laying paint, throwing paint, and creating masterpieces like this, Blue Poles. And now Richard Taylor is the person who's done all the work on authenticating Pollock. So he's a physicist by training, but he's also an artist. He took a year off somewhere in the middle of his postdoctoral studies to return to art school, in fact. And one thing that when he went back to art school, one thing that he was very interested in was he noticed in his work on nanostructures, on particular sorts of electron transport, I think, he was noticing that he was making certain patterns that were fractal-like, and not only, and I'll get to what fractal is, but patterns that looked much like Pollock's work. And he thought, that's so strange. How could that be happening? And so when he took this year off to paint, one thing he wanted to try to do was to try to sort of paint like Pollock. Now, he didn't succeed so well, but for his final project, he did the following thing. He went out into the moors of Yorkshire, of all places, with some of his friends, and they hung a large branch, in fact, in between two trees, and they built a pendulum. And from this pendulum, what they were going to do was, so the pendulum was driven by a sail. Okay? He then hung a sheet and attached it to the pendulum. And the idea was that the sail would drive the pendulum, and the pendulum would drip paint onto a canvas. Okay? This was how he was going to construct a Pollock. And lo and behold, he made this beautiful painting that he thought, my God, that looks very Pollock-like. So he got this idea that somewhere in the patterns of the wind, which we'll discuss are fractal-like, that he might actually be able to sort of channel Pollock. So for him, this was this sort of interesting conjunction of his work and his interests, and led him to see that there was a mathematics of Pollock. So how do we make math out of this kind of painting? And so Richard's idea is that the math is the math of fractals. So fractal geometry is often called the geometry of nature. So people think geometry, they think Platonic geometry. They think perfect shapes, beautiful straight lines, perfect circles, which we know is sort of a pale imitation of what the real world gives us. The real world gives us jagged lines and swirls and weird edges and crenellations, and which in fact can be quantified. That was the interesting discovery, maybe not completely due to Mandelbrot, but certainly made most famous by Mandelbrot in the 60s, where he coined the term for these natural sorts of structures as fractal, meaning fractional dimension. So a line has one dimension. Okay, you ask along a straight line, how far along that line am I? That's one number. Okay, a plane has two dimensions. Okay, I need two numbers to assign myself a point in the plane. And Mandelbrot realized that there was a way in which he could assign a number in between 1 and 2, so some fraction for natural objects, okay, which he called fractal. So natural shapes have an interesting property generally, that they exhibit something called a self-similarity on scale. So in this picture here, I'm constructing what in the end is the Koch snowflake, but it's constructed in a very algorithmic and repetitive way. I put this little triangular divot in a straight line, and then every time I have a straight line, come back arrow, here's a straight line, here's a straight line, here's a straight line, here's a straight line, I put another little kink in it. Okay, and I keep repeating that. Now I have straight lines here everywhere, and I put another kink in it, and so on and so forth. In the end, I get something like a snowflake. Okay, so natural shapes have some sort of self-similarity, you might say, and so the question is, how can I measure it? So you can ask the following sort of question. How long is the coastline of England? This is a question asked by Richardson, and you can see from this little illustration here that the answer depends on the ruler you use, right? If you use a very long ruler, it's all right, it's that long. If you use a shorter ruler, you're getting a better approximation, and a shorter one, so on and so forth, okay? So by some measure, it's infinitely long is the paradox. But it's clear that it depends on the ruler, and what fractal dimension measures is the relation of the ruler length to the distance that you actually measure, okay, of the object. So it's some fixed relation between those two things, and what you hope is that as the rulers get shorter and shorter, and the length presumably gets longer and longer, that those two numbers stay in sync in some way. And the way in which they stay in sync is the fractional dimension, when you can compute it. You can see it depends on some limiting process, rulers getting shorter, lengths getting longer, kind of thing. So in 2D, like an image, I'm not going to measure with a ruler anymore, right? I'm going to measure with a box. Okay, so in this case, instead of asking for how long is the length of the coastline, I'm going to ask how many boxes of a fixed size do I need to cover the paint in a Pollock image. Okay, that's the two-dimensional analogy, and I'm going to let the boxes get smaller and smaller, and presumably the area gets larger and larger, and again, these should stay in some fixed relation, and that relation will be the fractional dimension. So here's an example with a square. Okay, so a square requires one big square, or 4 half-size squares, or 16 quarter-size squares, and so on and so forth. So generally speaking, I need r to the d squares of size 1 over, I need r squared squares of size 1 over r, which would give me, you'll be happy to know, a dimension 2. Okay, a square is two-dimensional. So the definition agrees with your intuition. Now, what about for natural things? So here's a spiral galaxy, standard example of something with a fractal sort of shape. And the way in which you do this box counting, so here are the big boxes. The question is the galaxy in the box or out? So the white region shows you all the boxes, big boxes that contain the galaxy. Now the boxes get smaller, 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 and smaller. Okay, but better and better approximations, presumably. And here's something, a fractional dimension between 1 and 2. So now a Pollock example. So here's Pollock's full fathom 5 that Jim Coddington at MoMA shot for me. And with my friends Yang Wang and John Elton at Georgia Tech, we did it's a little more involved, but we did a sort of simple fractal analysis of this. Now, to analyze the painting, you have to do several things. First, you have to decide which color you're going to look at. So you have to do some layer extraction work, and that's actually a subtlety. So to get the black, you have to decide what's black in there. There are various gradations of black. Okay, what's white? Are you going to allow something that's a little gray to be white? Okay, so pulling the layers out is non-trivial. But if you do that, so here's one region here's the black layer, okay, which again the black is white, okay, because you're getting it's the high intensity. Okay, here's the white layer, and there's a silver layer in full fathom 5. So you do layer extraction, and then you do this box counting stuff. And what you get is you get fractal dimensions after you extract these sort of, the pure black part of the painting, the pure white part, the pure silver part. And here are some graphs that are proof of that. And now Richard's done this for a large collection of I think he's done 53 Pollocks. And Richard does many more things besides just the layer extraction. He's actually discovered various other characteristics when he does these fractal dimension computations. And in some interesting work that he's done very recently with physiologists are now discovering that if you're balancing on an edge, so Pollock would paint like this, reaching over. And it's actually known that Pollock was quite clumsy. Okay, in spite of these great films, he wasn't dancing around the canvas. He was lumbering around the canvas. And so when he would reach over, he'd be shaking a little bit. And some physiologists are able to actually tie the way in which you shake at the point where you're just at balance, okay, to certain fractal patterns. So Richard's been trying to tie some of Pollock's working style to this science, which I should say is a sort of important thing. I mean, anybody can just run numbers. So you should have reasons that you believe these numbers make sense. Okay, so with the help of physiologists and with connoisseurs and experts, they're trying to tie all these different pieces of the puzzle together. So here are some calculations. think these are both on, this is on the white layer, in fact. It should be, it's 1.72, forget the 1.98. And so Richard, over time, discovered that it actually seemed that this fractal dimension could be a signature. Now, Jim Coddington, the head conservator at MoMA, suggested to Richard in 1999 that maybe this would be a useful authentication tool. So Richard got in touch with the Pollock Foundation, and since about 2000, he's been a consultant for Pollock. They believe in him well enough that he's officially somebody that they send disputed Pollocks to. So Richard has looked at 46 Pollocks over his lifetime. He can't tell you how many were or weren't. So he was asked to weigh in on this collection. And so it's on the web now, but most of you will see this for the first time, I guess. So Richard has run the numbers, and he's looked at 6 of the drip paintings that Matter found, and they don't pass the test. People were suspicious for many reasons, and they remain suspicious. But they don't pass the quantitative test. And the foundation will be very careful now to say that this doesn't mean anything because everybody's worrying about being sued. I mean, if it's a Pollock, it's worth $10 million. If it's done by some guy with a stick and paint, it's worth $1.50. So but this is simply a statistical comparison, and that's what the statistics say. And so what's down the road for these paintings, I don't know. But Richard's had this, he's known this for months, and there was a lot of very nervous lawyers actually kept this quiet. I'd like to conclude that by saying, so in a digital world, style is a mathematical and statistical thing. Literary stylometry has been around for a long time, but visual stylometry is just beginning. And it's fun if you like art and math. I have to say, and as an aside, there's nothing better than if you're an art lover. And I think there's some people here from the museum, and I'm often so envious of you. There's nothing better than to be allowed behind the door in an art museum and see a great work of art. I mean, there's something weird because, when you're in the museum, you're just as close to it. But somehow when you're behind the door and it's there on the table, it's being conserved or something, it's a total thrill. So the work is a lot of fun, but I think, we're only at the beginning and it's a wide open field. So for people who have that inclination, it's a great thing to think about. So I have a lot of people to thank, and they're all here, and I have you to thank, so thanks.
I just love a lecture with alacrity by a blunt. We have time for a couple of questions.
Okay, you used a 50-dimensional space and not 40 or 60. I'm wondering, was that number actually somehow based on the data, and how much difference would it make if you chose a different one?
Sure. So I believe in the literature stuff they used 50 dimensions, and because there were presumably if you would use more dimensions, I mean those are the most common ones. So the ones that you're excluding by not taking 60 function words, for example, are words which are hardly occurring at all. And so those are telling you immediately that those dimensions, if you like, are just not important, sort of for what corner of space you're in. So in the painting stuff, the interesting thing is that we didn't really cook up any dramatically new techniques in the sense that we used mainly what my colleagues have been doing for photography, which has worked quite well. And they had various reasons for only going so many scales and only using so many statistics. And again, for the sorts of statistics that you get for those wavelet coefficients, you really need what we would say are only the first 4 moments to pretty well describe what the distribution looks like. So presumably more information wouldn't have helped you much, and especially after the dimension reduction, because you get rid of a lot of stuff by doing it anyway. Yeah?
Some artist styles change over time.
Right.
Has this ever been applied to an artist that has, say, lived 65 years and who started out stylistically in one way, like Picasso, and moved totally in a different direction? Have they explored that yet, or is it?
I mean, really, nobody's explored anything. So I mean, it's true. So the work that Luslavsky did, for example, looking at all of Plato's dialogues, nobody's done a similar thing. I mean, Richard's done some of this for Pollock, and he can track a change in fractal dimension, which, if you know his work, you would guess anyway, because he gets blobbier over time. All right, and so this is a way to quantify that blobbiness. But so suppose you had a sample of all of Pollock's works, okay, and maybe and you might get some nice, beautiful, smooth curve, and that's the interesting thing. So if somebody says, "Look, Pollock painted this in '52," and you look at it, it's sort of here. The curve is here, even though it's a reasonable number. So the short answer is that hardly anybody's done any of this work in any realm. But for Pollock, Richard does have a pretty good idea of how the numbers track. But the other point that would you expect to get the same numbers from Picasso's early period and his later period? Probably not. And that's why often when this work gets reported, it gets reported as mathematicians are pushing connoisseurs out of their jobs. And I mean, it's totally crazy, because first of all, we can't do this work unless connoisseurs and historians are interested in it. And second of all, you can't do it independent of the knowledge of the art history. So I mean, you just have to be sensitive to that. I wouldn't expect a digital picture of Biedermeier's 3D pieces, his constructivist pieces, to be anything like his cubist stuff, right? It's you have to be smart about it. Yeah.
Now, Bruce announced the talk tomorrow.
Sir, one more question.
Sure.
Yeah. I heard about a month ago that some scientists had analyzed the Mona Lisa and found out something like they're 88% certain it was smiling. Did they do it? Do you know if they used the same method to find that out?
I'm afraid I don't know anything about that.
Okay, so before you go, let me just make a couple of little announcements and connections here. So you have another chance to hear Dan talk about a quite different nexus of art and mathematics. He's going to give a talk tomorrow at the Wiseman Art Museum at noon. I think you can bring a sandwich if you want. And he's going to talk about mathematics, the maker and muse of modern art. So it's ways in which mathematics inspires and enables modern art. And everybody's invited. A couple of things came up in the lecture that Dan pointed out, that we're having a workshop right now going on at the IMA. This is at the level of, this is called Mathematics and Art of Film Editing and Restoration, and it's aimed for the people who really get their hands dirty trying to fix films and edit films. On the one side, coming from the film editing world and Hollywood and so forth, and the other side, the mathematical world. We saw a picture of Wizard of Oz, and today I had the pleasure of seeing somebody from Warner Brothers who had taken the very original prints of the Wizard of Oz and done some unbelievable mathematical algorithms to those to produce the most beautiful picture of Judy Garland you can imagine. He had a similar feeling about what a great pleasure and a privilege it is to deal with these original objects. He also made a comment that really captured what the IMA is about, so I'm going to repeat it. He said, if you've worked on radar imaging, it's the same stuff. And actually, that's what we did in the IMA earlier this year. We worked on radar imaging. And that's the key thing about the Institute for Mathematics and its applications. The math there is really the thing that connects it all together. And I think we saw some of that in this talk here. There'll be some more coming up. The next public lecture will be by Arlie Petters, who's one of the world's foremost experts on gravitational lensing. His talk is called Gravity's Cosmic Shadows, a Mathematical Unveiling. That's on March 22nd. Arlie is a wonderful guy. And then on April 19th, the final lecture will be by Dan Rockmore's thesis advisor, Percy Diaconis, And he's going to talk about mathematics and magic, and I guarantee it'll be a great deal of fun and very informative. Hope to see you both there.